Students, after the chapter Mechanical Effects of the Solids, we are going to start our chapter, that is chapter 2, Units and Measurement of your syllabus. In this chapter, we will study about the physical quantity, and basically the physical quantities are divided into two further types, the fundamental and the derived quantities. Then units, fundamental and the derived as well for these physical quantities, characteristics of standard units, FPS, CGS, systems, SI system of units, definitions of all these basic physical quantities, the definition and the methods to measure these physical quantities like the distances, like the mass and the time. After that, we are going to discuss about the accuracy and precision of the instruments in order to measure the physical quantities and the error associated with these measurements, and we'll study about various types of error and their combinations. After that, significant figures, their scientific notations, dimension, and at the last, we'll practice to derive the dimension formulae and the dimensional equations and the applications of dimensional analysis. So let us begin with our first topic, that is physical quantity. Now, what is a physical quantity? A physical quantity is that quantity which is measurable. That is, we can measure a quantity like the mass, the time, the length, the intensity of light. So there are so many physical quantities around us. Now these physical quantities can be further categorized into the fundamental and the derived quantities. So what are these fundamental quantity? Basically, a physical quantity which is based, that is the base, and which cannot be derived from any other quantity is known as the fundamental quantity. For example, we are having mass, we are having length, we are having time. So these are the base quantity and fundamental. We use these quantity to derive other quantities, like mass is a base quantity, but if we are multiplying this mass with velocity, and of course the velocity is also a derived physical quantity, that is, it is having two base quantity, that is meter, that is length, and time, second square. So we are using two base quantities in order to get one derived physical quantity, that is known as velocity. So derived physical quantities, we can define them that these are those physical quantities which can be derived or expressed from the base or the fundamental quantity. So there are so many examples around us, like the speed, velocity, acceleration, force, momentum, torque, energy, pressure, density, thermal conductivity, resistance, magnetic moment, etc. So we are having so many other quantities which we can derive using the base fundamental quantities. Now, after discussing the fundamental and the derived quantity, we need some measurable quantity or entity to define or express these physical quantities, and that is known as the unit. So what is a unit? The measurement of any physical quantity, it involves comparison with certain basic, arbitrary chosen, internationally accepted references, standard. These are called the units. So as we know that we can't say that our mass is in kg and our length is also is kg, so we need different unit for different physical quantities. So like as we are having two types of physical quantities, that is the fundamental and the derived, similarly for these types of physical quantity we are having separate units, like we are having the fundamental units, and the fundamental units are the units of fundamental or the base quantity. So we need some units to define the amount, the quantity of a fundamental base, and these are called the fundamental units. For example, we are using meter for length, kilogram for mass, and second for time. Similarly, as the derived quantities are obtained with the help of base quantities, so we are having the derived units as the unit of derived quantity which can be expressed from the base or fundamental quantities, and these are called the derived units. Again, like we are having meter per second, that is for speed or velocity. For density we are having kg per meter cube. For force we are having kg meter per second square. For acceleration we are having meter per second square. For momentum we are having kg meter per second, and so on. So we are having separate units for the physical quantities, for each and every physical quantities, whether they are the fundamental or the derived. Now, in order to define or explain both the fundamental and derived units, we need some system of units. So for that we have a system of units, and this is a complete set of both the fundamental and derived units. This is known as the system of units. Now there are some characteristics of the standards in order to obtain a system of unit or define the units for these physical quantities. So let us discuss the characteristics of the standard units. So a unit selected for measuring a physical quantity must fulfill these following requirements. Number one, it should be well defined. That unit should be well defined. Number two, it should be of suitable size. That is, it should neither be too long nor too small in comparison to the quantity to be measured. Number three, it should be reproducible at all the places. We can reproduce those units at all the places. Next one, it should not change from place to place or time to time. So they remains constant everywhere. It should not change with physical conditions like the temperature, the pressure, the volume, etc. And last but not least, it should be easily accessible. Now, in our day-to-day life, we are using various system of units. From place to place, earlier, they vary from place to place. So, we need to define some standard in order to that they can be easily accepted internationally everywhere at the same time. So in earlier time, various systems like FPS, CGS and MKS systems of units were used for measurement, and they were named so from the fundamental units in their respective systems. So we are having a table to discuss these systems of units. So in first column you can see that we are having the quantity, then the dimension for that quantity, and the system of unit related to that. So first one is the length, and the dimension for length is L. So FPS system, in FPS, that is foot, pound and second system, for length we are using foot. In CGS we are having centimeter, and in MKS we are having meter. For mass we are having the dimension M, but in FPS the unit for measurement of mass is pound. For that length, or for that CGS system, it is gram, and for MKS it is kilogram. And similarly for time, the dimension is T, and in FPS system time is measured in second, CGS is measured in second, and MKS again the time is measured in second. So we can observe from this table that for these three system of units we are having three different units for length, for mass, although it is same for time, but we are having different for the length and mass. So it is creating a lot of problem, because earlier some people were using this FPS, some were using CGS, and some were using MKS. So in order to get a unique and internationally accepted system, we define the SI units, because a very simple example is there, that a name onion is given to onion, but somewhere we are using that pyaz, somewhere we are using kanda, somewhere we are using different name for a single. So a name should be given which is internationally accepted. Like in case of the length measurement, if we are saying that some people are using that palm length in order to obtain the length or total measurement, some are using the foot, some are using inches, and some are using so many different scales. So we need a scale which is same internationally. Now what is the drawback of using these different units is that, suppose a person is working on an experiment and he discovers something, or he invents something new. It might possible that some other person in other part of world is doing the same experiment, performing that, and figure out something new. Now in order to differentiate between the discoveries or inventions they obtain, we need some standards so that they can define that they are obtaining whether the same thing or the different thing. So for that we are having the SI units, that is System International Day Units. This is the full form for this abbreviation. Now this SI system of unit is accepted internationally. The SI system with standard scheme of symbol, units and abbreviations was developed and recommended by the General Conference on Weight and Measurement in 1971 for international use in scientific, technical, industrial and commercial work. And this is accepted internationally. Now this SI system uses decimal system, and therefore it is very convenient to convert the system of unit, that is one system to another system. We can easily convert the units. Like 1 meter is having 100 centimeter. So 1 meter is 10 raised to power 2 centimeter. Similarly, for the mass, 1 kilogram is having 1000 milligram. So 1 milligram is equals to 10 raised to power minus 3 kilogram, or 1 kilogram is equals to 10 raised to power 3 milligram. So the base is 10, that is decimal. Now we are having a fundamental system of units for the main physical quantities. So we are having some base or fundamental physical quantities which are used to derive further derived physical quantities. And let us have a look. So we are having basically 7 main units which are used or said as the fundamental or base physical quantities, like the length, mass, time, electric current, thermodynamic temperature, light intensity, amount of substance. And for these we are having the symbols SI units and the symbol for the units. So length is L, capital L is the symbol. SI unit is meter, symbol is small m. For mass, symbol is capital M. SI unit is kilogram and the symbol is kg. And you are very well aware of these SI units because we had already studied. We are studying these from our earlier classes as well. For time we are having the symbol T. SI unit is second, symbol is S. For electric current it is ampere and the symbol is A, and the symbol for SI unit is again A. Then thermodynamic temperature, we are using temperature in degrees Celsius and Fahrenheit in order to use the temperature or measure the body temperature in our day-to-day life. But the standard is Kelvin and the symbol for that is capital K. Light intensity is measured in candela. SI unit is candela and the symbol is CD. Amount of substance, you had already studied in your chemistry that symbol is mole and the SI unit for amount of substance is mole. In terms of Avogadro's number, you have already studied, and the symbol for SI unit is again mole, that is MOL. Now there are some supplementary units also in order to define some other physical quantities, like the plane angle we are using. We had studied the angles in case of triangles, in case of that Pythagoras theorem. So the symbol for angle, plane angle is theta, d theta, that is for small angle. SI unit is radian and the symbol is RAD, radian. Another supplementary unit is the solid angle. Now plane angle is used to measure angle in 2 dimensions, but the solid angle is used to measure the angle for 3-dimensional objects, and the symbol is d omega. SI unit is steradian and the symbol is SR. So after discussing these fundamental units in the SI system, let us define these SI units we are using for these fundamental physical quantities. So let us discuss about the definition of SI units. Let us first take meter. Now what is meter? We are having a scale 100 centimeter over there and we measure the length. So meter is used for measurement of length. Now from where this meter is being derived? So the meter is defined as, we are taking a fixed value of the speed of light in vacuum, that is 299799458. Now this is somewhere equal to that we are using for our numerical problem, that is 3 into 10 raised to power 8 meter per second. So when this speed, this fixed numerical value is expressed in meter per second, and when this second is defined in terms of cesium frequency, that is the frequency of cesium radiation, then we say that this particular value is meter. Now earlier there was other definition for meter, and that was that the meter is the length of path traveled by light in vacuum during the time interval of 1 by 299792458 of a second, and this was given in 1983. But now we are using some fundamental constants like the Planck's constant, like the frequency, like the charge in order to derive or define the SI units, and this was recently changed 2 years back. That is, the definition of meter was changed. Next unit is the kilogram. Now the kilogram is used to measure the mass, and it is again changed 2 years back. That is, it is defined by taking the fixed numerical value of Planck's constant to be 6.62 607,015 into 10 raised to power minus 34. Now when this Planck's is expressed in joule second, so this is SI unit for Planck's constant, and which is equals to again kg meter square per second. And you know that what is kg, what is unit for that length, what is unit for second, and all these are defined in terms of the speed of light and the frequency of the cesium atom. Earlier the definition of kilogram was that kilogram is equals to mass of the international prototype of kilogram, that is a platinum iridium alloy cylinder, which is kept at International Bureau of Weights and Measurement. It served near Paris, near somewhere in Paris, that is in France, and it was defined in 1889. Now the next is the second, and how we define second. That second is that duration of 9192,631,770 periods of radiation corresponding to the transition between the two hyperfine levels of ground state of cesium 133 atom, and it was defined in 1967. That is, we are having hyperfine two levels, two bands of these cesium 133 atom, and this is the time taken by the radiation to transit from one level to the other level. Our next system or the SI unit is Kelvin, that is used for measurement of temperature, and the Kelvin is defined as that it is a fixed numerical value of the Boltzmann constant K to be 1.380649 into 10 raised to power minus 23 when it is expressed in terms of joule per Kelvin, and this unit is also been changed earlier. Now this is the recent unit we are using, but the earlier unit of the temperature was that the Kelvin is the fraction of 1 upon 273.16 of the thermodynamic temperature of the triple point of water, and it was given in 1967. Now we are defining this unit of temperature in terms of Boltzmann constant. Next SI unit is the candela, and this candela is defined as the luminous intensity in a given direction of a source of light that emits the monochromatic radiation of frequency 540 into 10 raised to power 12 hertz to be 687 watt when expressed in 1 meter per watt. Now this was earlier defined in terms of watt per steradian, that is in terms of solid angle, as we know that the light spread three-dimensionally, that is at the angle of 360 degree. The next unit is mole, that is used to define or measure the amount of substance in any object. So this is defined as 1 mole exactly contains 6.0222 into 10 raised to power 23 elementary entities. Now this is our Avogadro number. So this is a fixed value of Avogadro number. We are defining mole by using a constant, but earlier the mole was defined as the amount of substance of a system which contains as many elementary entities as there are atoms in 0.012 kilogram of carbon 12 atom, and this was given in 1971. And at last we are going to define one important SI unit, that is ampere. And you already studied that ampere is SI unit for current. We measure current in terms of ampere. So again it is changed unit, and it is defined by taking the fixed value of the elementary charge, that is 1.602176634 into 10 raised to power 12 when expressed in the unit C, which is again equals to ampere second. So this is the value we are assigning to ampere, but earlier the ampere was defined as that it is that constant for current, or that constant current which, if maintained in two straight parallel conductors of infinite length of negligible circular cross section and placed 1 meter apart in vacuum, it would produce between these conductors a force which is equals to 2 into 10 raised to power minus 7 Newton per meter of the length, and it was given in 1948. Now these are the definitions of SI units, and for your exam point of view you need not to worry about to learn these values. These are for your knowledge, that how these SI units we are using for various physical quantities are being defined, or how they have been defined. So after these main physical quantities, we are having again two other SI units for other physical quantities, that is for the plane angle. And this plane angle d theta is basically the ratio of arc ds to the radius r. So we are having an arc that is of length ds with some point O. So this angle is between these r and r with that point O, and arc is the length of from one end to other end. So this plane angle d theta is the ratio of this arc length ds to the radius of this circle we are obtaining this arc from which. So this SI unit is known as radian, but in case of that solid angle we are having something different. So this d theta is equals to ds upon r, and both are again if we measure, these are length, so we are having the unit radian is SI unit for this plane angle. Now if we discuss about the solid angle, for the solid angle we are having the SI unit as steradian, and let us discuss. We are having a figure, and this is a three-dimensional figure. We are having a cone instead of that a triangle, and this is the angle, that is d omega is the solid angle for this cone. Now dA is the area of that portion for which we are having this solid angle. So this solid angle d phi is the ratio of intercepted area dA of the spherical surface described by the apex O, that is the center, to the square of its radius, and its SI unit is steradian, and it is equals to d omega is equals to area upon the radius square of that spherical object from which we are taking out this solid part.